So now I'll talk about an example about electrolytes in electric fields, and this is where we're going to apply chemical potential right now. So electrolytes, those are systems where ions are mobile and can carry charge. So one example is the lithium-ion battery that you've got in your computers, in the cars, and in them more or less everywhere nowadays. They've got lithium ions that are mobile, that are going through solid electrolytes, so that they go from an anode to a cathode and carry charges. And more exciting perhaps use of this is nerve impulses in the brain. Our brain is a connection of nerve cells, and these nerve cells actually have electrical signal sending, and this means that across the membrane of a nerve cell there is a potential energy difference with ions heaping up on each side, and this the electrical potential with the ions is what is carrying the signals in our nerve cells. So to signify this, I've started drawing a small electrolyte, or a small electrolytic cell. So this box is our cell, and inside we've got some positive and negative ions, and in this example the positive ions are mobile, they can move around, whereas just like in the lithium-ion battery, and the negative ions, they are stuck in the place. And we've got two electrodes, one on each side of the cell. These electrodes are connected to a battery, giving a potential difference, so that there is an electric potential across the cell. So if we now say put in space axis here, the one end of the cell is position x equals 0, the other end of the cell is x equals L, which is the length of the cell. And the potential energy difference, or the potential, not the potential energy, but the electrical potential at L is V of x equals L. We'll call that just phi of phi. And as I said, the positive ions, they're mobile, and the negative ions, they're fixed. So let's just before starting this, let's recap a little bit electricity and about electricity. So the electrical potential we can have an electric potential around a charge, for example. So if we've got a charge with a charge Q, then at some distance r around the charge, the electric potential around as a function of this distance equals 1 over 4 pi times the susceptibility of the medium times the charge divided by the distance. Now, for a homogeneous field, like in our example with the electric cell, so between the electrodes, we know that it's homogeneous. So from one end of the cell, x equals 0 to L, it goes from 0 linearly up to the value at phi of L. So we can write phi of x equals x over L phi of L. Or we'll just write it as phi L for short. Now the electric field inside of the electric field is just defined as E. It's a vector field. It's minus the divergence of the electric potential. So around a charge, it'll be 1 over 4 pi epsilon as before, q over r squared, and then times the unit vector outwards. And in a homogeneous field, homogeneous one-directional field, it's just E field is just the potential over L. Sorry, I forgot the minus, and there should be a minus here and there as well. So this equals minus phi over L. So the electric field is the same everywhere because the slope of this line is the same all the way. So there's a homogeneous constant electric field as we start out. Let's say in this cell that we've got here, then we start out with a homogeneous distribution of ions, and as we switch on we connect it to the battery, there is an electrical potential and a homogeneous electric field. Now, the thing is that this electric field, it will give a charge, it will give a force on the charges. And this force is proportional to the electric field, and then proportionality constant is the charge. So this means that once we turn on the field, all the positive ions, so if we've got put on minus here and plus there, all the positive ions will feel a force to the left, and all the negative ions will feel a force to the right, but the negative ions are stuck. So it means that all the positive ions will start moving. And the question I'm posing today is, how far will they move, how will the whole system develop? Clearly, as we switch them on, they will all feel a force, and they will all start to move. Now, in order to find out how they end up, maybe we're not able to find the whole dynamics, but at least I'd like to find out what is the equilibrium situation. And for this, I'd like to know the potential energy of a charge in the field, because then with the potential energy we've got something that we can evaluate to get the equilibrium condition. So the potential energy of a charge inner field. That's an electric field. That's so we have so the force can be expressed as the minus the divergence of the potential energy. So QE equals minus Q times the divergence of the potential, which equals minus U. So from this we clearly see that we can express the potential energy as simply the charge times the electric potential. So from the electric potential we also then have the potential field. So as I said, we now would like to find the equilibrium distribution, and or the equilibrium state, and as we saw they will start moving, but because all of them have a charge around them, there will be a field around each charge. Then having a non-homogeneous field of ions will affect all the ions, will affect the electrical field. So clearly, as these ions are moving, then we will heap up with more positive ions on this side, and there will be fewer positive ions on this and on the other side, and this will continue. Clearly this will continue until the electrical potential from the ions themselves counterbalance the outer electrical field. So we can guess that the distribution of ions will be around the original distribution, where and the number of, or the density of positive ions equals the density of the negative ions, and that close to the one electrode at x equals 0 there will be a surplus, and close to the other electrode there will be less. And then this means that in the middle there is n0, where n plus equals n1, and there is no electric field anymore, because as long as there is an electric field there will be motion of ions. So equilibrium clearly means there is no more motion, it's all stopped. And we'd like to know, well, how does this distribution look like at the edges? But it will be something like this, but we'd like to know more in detail. So it's an equilibrium. We're looking for equilibrium. That has to do with the number of particles. So it's clearly a chemical equilibrium, and so we're looking for the chemical equilibrium. Which means that we need to find the chemical potential. So the chemical potential in an electric field the electric field is an external field, so we know then that the chemical potential has to be a function of the internal chemical potential plus the external chemical potential. And we've already seen that this is some reference chemical potential, which is a function of the equilibrium distribution, equilibrium concentration that we started with, plus kT times the logarithm of the concentration distribution divided by n0, because this reference is the one we divide by here. And then the external part, well, that's the potential energy per particle in the electrical field, which we just found to be Q, and then charge times the electrical potential. So the equilibrium condition, that's just that the chemical potential is a constant. That's because if the chemical potential is not a constant, then things will be moving. So we can also express that as that mu of x equals 0 equals mu at L. But of course it should be all the way. So we can put that into the expression for the chemical potential. So then we get kT logarithm of n0 equals kT of the logarithm of n of L plus the charge at L, charge times the electrical potential at L. Now this we can just rewrite in very simple terms. We take these ones and divide, and then we what happened now? And we see that we can, and so we divide by kT and exponentiate, and then we've got this equals the potential energy over kT. So as we said, we already guessed that this is an anti-symmetric distribution. So we're guessing that in the middle, for example here it's L half, then we expect it to be the average concentration, and then, and of course this average concentration, the concentration at each side should be have the same deviation from the average concentration, so that the height of each of these peaks here should be the same. It should be absolutely anti-symmetric. The amount of charges we are moving from one side has to match the amount of charges we are moving to the other side. So this we can then rewrite this condition as n of 0 equals 2 times, so we multiply by 2 on both sides here, and we've got 2 minus n L And then we can take this expression here and put it together with the last one, and we get n of 0 over n of L equals 2n0 over n of L minus 1. And from here we get that this equals e, the exponential of the electrical energy, the potential energy, over the thermal energy. Now let's try to get the values at the end. So n of L should then be 2n0 over 1 plus e to the q phi over kt, and just turning it around, we've got n of 0 equals 2n0 1 minus 1 over 1 plus e to the q phi over kt, which gives us 2 over n0 1 plus, so I'm just multiplying on top and bottom and adding them together, q phi over kt minus 1 over 1 plus e to the q phi over kt, and then we can remove these two, so we get a nice expression for 2n0 over 1 plus e to the minus q phi over kt, because I've divided by this guy, and then we get the minus. So so now we see that the distribution around n0 from 0 to L in the x direction, it starts out, so let's call this n of 0, and there is n of L, which we have expressions for, and we see that there's an exponential decay towards the middle, and here's L half, and the same on the other side. Well, it didn't look very asymmetric, but it's supposed to be asymmetric. So, and we see that the width, the width of this decay, that's related to the relation between the electrical field and the thermal energy. So it's how far in, if at very low temperature it'll be a very sharp distribution, so then the ions will tend to go all the way into the edge of the box. But as temperature rises, they will be pushed further and further out by the thermal fluctuation of the ions. They cannot sit still. So finally we can then write the chemical potential as a function of x as kt, the logarithm of n of x over n0 plus q phi. which gives us a, turning this around, we get the distribution, the whole ion distribution, which is n of x over n0 equals e to the q phi minus mu 0 over kt. And so, and this is mu 0. So we see that the strength of here we see the Boltzmann factor. Oops. Here we see the Boltzmann factor with the chemical potential in it, due to the fact that that we can move the ions, and we'll see this more next week. Next lecture when we're getting to the Gibbs factor.